the next talk of Dr. Ramesh C Vats of NIT Hamirpur. So over to Professor Dr. Shankar Raj.
Just one second. Okay.
वो क्या करना पड़ेगा भाई? इसमें फुल स्लाइड करने के लिए क्या करना पड़ेगा? कंट्रोल एल। ठीक है कंट्रोल एल कर दी। स्क्रीन शेयर करूंगा फिर मैं पहले स्क्रीन शेयर करूंगा।
Dr. Shankar Raj, could you get your mic is mute? Could you get his?
Yes, sir.
In the booklet, it is there.
Yes, sir. Yes, sir.
If you want, I can.
So here we are going to have second session of the last day.
I think you go to mute, sir. You are in first parallel session also. I think so.
Three talks are there. First one by Dr. V. Shankar Raj, then by Dr. D. Gopal, then by.
Okay, sir. Shall we start, sir?
Yes, please start.
On behalf of the organizing committee, I invite Professor R.K. Vats, Dr. Ramesh Kumar Vats, former head of the Department of Scientific Computing, NIT Hamirpur. During his tenure, headship, 2 programs have been started, one PG Mathematics and Computing and one undergraduate program in Mathematics and Computing in NIT Hamirpur. He has more than 20 years of experience of teaching and research. He has published more than 75 research papers in various international and journals in a reputed and attended more than 25 national, international and national conferences. He has visited USA, Russia, Turkey and South Korea. He's guided 10 students for his PhD thesis and 7 students for MSc degree. He had handled 2 external funded agencies for more than 25 lakhs. He organized 15 short-term course, workshops, conference in NIT Hamirpur. He is a life member in various professional societies and he is a reviewer of various international journals. He held various administration positions in NIT Hamirpur. And with this short introduction,
your slide is not coming, Dr. Vats. Is it coming there?
Just a minute, sir.
Okay.
Okay.
So with this introduction, this short introduction, I like to hand over the session to Ramesh Kumar Vats, Professor Ramesh Kumar Vats.
I think it is all right. We are running late.
Yes, sir.
Thank you very much, sir.
Yeah, really, it was really illuminating talk in the area of fractals. So I thank Professor Masopust from the.
Thank you very much for inviting me. I am highly thankful to the organizing. May I start, sir?
Yes, sir.
I am highly thankful to the organizing committee for giving me opportunity to share my views on the controllability of fractional order system, and my special gratitude to Professor T. Shom, who gave me this opportunity specially to me. Now, should I start, sir?
Yes, sir. Please. Yes, sir.
Okay. Title of my talk is Controllability of the Fractional Order System. And the basic contents of my talk is, first is a fractional calculus. What about the brief introduction of the fractional calculus? Second one is the fixed point theory. And third one is the controllability. And fourth one is the controllability of the fractional order system using the fixed point theory. And finally, we conclude what about the conclusion of using all these concepts in the using the fixed point theory. And first is what is the fractional calculus? Before going to the fractional calculus, that is, you can see in the C, this is a stone which just a part of the stone is just seen. What we see often is only a fractional part of what is really is. Means we can see a fractional part of this because of this part. Then come to the portion of the fractional calculus. Why n in the nth order derivative has to be positive integer? Why this question arises in many of the mathematicians. And we also say that when this n is minus n, then it equivalent to be the nth fold integral, because the nth order derivative is a reverse process of the n fold integral, which gives the identical functions. And it turned out that this question has been asked by the L'Hopital in the letter of Leibniz in 1695. What question has been asked by the L'Hopital? What would happen if we give n is equal to 1 by 2 in this nth order derivative? Then the Leibniz answered, this is an apparent paradox from which one day will draw useful consequences. That gives in the 1695. But after a time, nowadays it gives the useful consequences. We can see in 1738, Euler introduced this alpha order derivative of x beta. Alpha is a fractional. Alpha and beta both are the positive real number. It is equal to be the gamma of beta plus 1 divided by gamma of beta minus alpha plus 1 into x raised to the power beta minus. This is the alpha order derivative of x raised to power beta it gives by the Euler, which is a formal generalization of the elementary fact, that is nth order derivative of x raised to the power m is this one. And this factorial m, if it is equal fractional order, then it converted to be the gamma function. And if this alpha is a positive integer, then it is gamma of beta plus 1 is a factorial m. It means it is a formal generalization of this elementary fact. Around 1830, Livoli considers functions that can be written as series form. And Livoli consider a function which can be represented in terms of the exponential series. And derivative of this exponential series of alpha order is equal to be this, that is a raised to the a power an alpha n raised to the power alpha and e raised to power alpha n x. This is the derivative of the function which can be represented in the form of the exponential series. But these definition leads to be controversies. What controversy is given by the definition? You can see. Let us now compare this with the definition given by the Euler to see if they agree by Taylor series. The expansion of e raised to power x by using the Taylor series is this summation and 1 by factorial and x raised to the power n. By Euler definition, the derivative of this e raised to power alpha, e raised to power x with of order alpha is equal to be like this. This is by the definition of which is not equal to e raised to power x. As we know, the derivative of any order of e raised to power x is e raised to power x, but it is of using the definition of the Euler, it is not equal to be e raised to power x. Hence, by Livoli definition, by using the Livoli definition, derivative of e raised to power x of order alpha is e raised to power, which is a contradiction. In 1823, Abels considered the Tritocon problem and posed his solution in terms of the integral equation, and later on this problem was considered the first application of the fractional calculus, which was pointed out by the Leibniz in the 1695. This is the Tritocon problem, and a ball is dropped from any place in this trajectory path, either from this blue point place, or from the red point place, or from the green point place, or from the yellow point place at the same time. It reaches at the bottom point at the same time. This is the proper application of the fractional calculus, which is named as a Tritocon problem. This is the initial stage when we would like to drop the ball from these positions at the blue point position, red point position, green point position, and yellow point position. This is the final stage when they reach at the same time. In mid of 19th century, Riemann and Livoli introduced the fractional derivative of like this. This is the definition of the fractional derivative that is named as a Riemann-Livoli fractional integral. First, they introduced the fractional integral. Then, using this fractional integral, they define the fractional derivative. Using the fractional integral is to be defined using the n-fold integral, which is named as the Cauchy integral formula of n-fold that will convert it to a single integral. Using this single left and right hand side single integral, this define Riemann-Livoli fractional integral. The Cauchy formula for the repeated integration compress n times integral of a function into a single integral of n belongs to the integer. The Riemann-Livoli fractional derivative of alpha is defined as initially first they defined the Riemann-Livoli integral, then they defined the Riemann-Livoli fractional derivative. In the definition of the Riemann-Livoli fractional derivative, they use their fractional integral which they defined earlier. In 1967, Capito introduced the Capito fractional derivative by exchanging the order of the derivative and fractional integral. The Capito fractional derivative of order while defined by this one. This is the definition of equation number 8 is the definition of the Capito fractional order derivative in n alpha lies between n minus 1 to n. It may be n. There is a relation between Riemann-Livoli and the Capito fractional derivative. This is the left hand side. I have given this Riemann-Livoli derivative, and right hand side it is a Capito fractional order derivative, and this is the relation between these two. Thus, the two type of the derivative coincides for zero initial conditions. Zero initial condition means when FIA will be 0, then these two integral coincides each other. The Hilfer introduced the new definition of the fractional derivative at the end of 20th century, known as Hilfer fractional derivative. It is also known as the generalized Riemann-Livoli fractional derivative. This is the definition given by the Hilfer in the end of the 20th century. The relation between the earlier definition, that is Capito and Riemann-Livoli, and between the Hilfer, this is the relation when this V is equal to be 0 and sigma lies between 0 1, the Hilfer fractional derivative becomes the Riemann-Livoli derivative. And then when this V is equal to be 1, then and sigma lies between 0 1, then the Hilfer fractional derivative becomes the Capito fractional derivative. It means the Hilfer fractional derivative is the generalization of the Riemann-Livoli as well as the Capito fractional derivative. And these are the applications of the fractional derivative: electric transmission lines, application in the control system, that is to increase the speed of response, to decrease the relative stability, eliminate the steady state errors. The fractional, this is the main model in the fractional calculus, which is very applicable to everywhere. That is Berkeley-Torvik equation of the oscillatory process with fractional damping. These are the notations which I mentioned. These are some basic references which give the application of the fractional calculus in the control theory and image processing, bioengineering, telecommunication, electronics, signal processing, economics. And now come to the point, because the fractional without the fractional derivative and the control system, fractional derivative using the definition, using the fixed point theory, we find out some problems. To come to the fixed point theory, there are fixed point throughout lifetime where things must stay exactly the way they are. This is the real life example of the fixed point. When I stir my cup of coffee, at least one speck of the liquid winds up exactly where it started. This is that point is named as a fixed point. These are the basic definition of the fixed point. Many of the speakers have already introduced about the fixed point. So I don't want to say more about the fixed point. What are the major application of the fixed point theory? This I have already, many of the speakers have already introduced. This is one fixed point, example of one fixed point, example of two fixed point, example of seven fixed point, example of infinite many fixed point. Then this is the main theorems which are to be used in the solution of the fractional order problems. The Schroeder fixed point theorem, that is, I think V. Shankar has already introduced this fixed point theorem. Then Sadowski fixed point theorem. Then condensing map, which is used in the Sadowski fixed point theorem. Krosner-Selsky fixed point theorem. This is already has been, I think, many of the Rajendra Pant and some more speakers have already defined what is these. And next point is the controllability. Next point is the controllability. You cannot control without being controlled. This is the quote. This is the journal life. You cannot control without being controlled. And you controlled yourself to control the other things. That means controllability is a fundamental concept of mathematical control theory. So before this, we throw light on the history of the control theory. What is brief introduction of the control theory is an interdisciplinary branch of engineering and mathematics that deals with the behavior of the dynamical system to achieve the desired goal. Means control theory means our aim is to control our system. Means what is to be desired, that is our main goal. Control mechanisms are widespread in nature. For example, in biological systems of the human body, our body temperature and blood sugar level need to be controlled at desired set points. Insect and animal population are controlled by very delicately balanced prey-predator relationship, and several man-made control systems such as missiles, nuclear reactors, automatic washing machines, and etc. All these things are to be controlled. However, whether the system is natural or man-made, they have a common aim, that is to control or regulate a particular variable within a certain operating limit. Control mechanism has been seen since ancient times. Some experts believe that the control theory is more than 2000 years old and the originated in the ancient Mesopotamia, where the control of the irrigation system was also a well-known art. The modern development of the control theory started during the 17th century. In 1656, the pendulum clock invented by the Christian Huygens was a modern example of the development in control theory, in which the problem of the speed control was analyzed. Control theory had gained remarkable impact and popularity in 1769 when James Watt invented the steam engine, in which a control mechanism is used, which is also a great example in a control theory. In the 1860s, Scottish scientist James Clerk Maxwell published the first mathematical description of the steam engine, iterated behaviors, and proposed some control mechanism. In the 1950s, powerful generation techniques of the control theory began to develop that allowed treating multivariable time-varying system and many other nonlinear problems. Control theory is nowadays being viewed from two perspectives: a theoretical foundation for control engineering, a subset of system engineering, and a mathematical disciplines. Now come to the next. how do I explain controllability to a layman? Everybody can see everything when you are when you would like to drive a car. If your speed is under control, then everything will be okay. When your speed is not under control, instantly you cannot control. When instantly you would like to brake the car, then it may not be uncontrolled. Imagine that we have a toy remote car in a room. We have its remote and it is built such that it can only move left and right from the bird's eye views. We also have a sensor on the left wall measuring the distance of the car from the wall, which we decide to call X. This you can see, this is a sensor and this is the distance of the car which can move only left and right. Since we have the remote, we can move the car by changing its position X. Thus, its position X is controllable. Imagine that we are interested in being able to make the car go to any point we want in the room. To be able to define any point in the room, we call the car's distance from the lower wall as Y, but since the car can only move left and right, we do not have any means of the influencing its position Y. Its position Y is uncontrollable. We thus we thus decide to upgrade the car, and now it can also be moved upward and downward direction, or you can say first is left and right, then in other directions also. You can see the now car can be movable in all direction, that is controlled from the all direction. Now we can also influence the car position Y, thus its position Y has become controllable. We decide to solve this problem by installing a sensor on the lower wall, and we apply sensor on this wall also and then this wall also. Then it can be controlled. Now its position X and Y both are controllable since we have means of the influence them via the remote and the car wheels controllability. Now, controllability is a fundamental concept of the mathematical control theory introduced by Kalman in 1960. Controllability is a qualitative property of dynamical control system that plays an essential role in developing modern mathematical control theory in finite and infinite dimensional spaces of the system represented by the ordinary differential equations. Controllability means that the dynamical system can be steers from an arbitrary initial state to any arbitrary final state with the help of some admissible control function. Means our aim is to get the final state with the help of some admissible control functions. The controllability of nonlinear system represented by evolution equations or inclusion system in abstract space led to some important conclusions regarding the linear and nonlinear dynamical systems. Many scientific and engineering problems are nonlinear and can be described in infinite dimensional spaces. So, the study of controllability in infinite dimensional space becomes significant. This is an example by on which one can motivate for the controllability. Consider a one-dimensional initial value problem. Then choose the final state x. When this t is equal to 2, it should be at 6. But initially, the trajectory of the system starts from the initial state 3 and does not reach the final state 6 in the interval 0 to 2. It reaches to be 6. We apply a control function, that is u of t, where we under this initial value condition, where u of t is defined by like this one, then we can see our system will be controlled and it reaches at the final stage which is to be required. The trajectory of the system 9 starts from the initial state 3 and reaches to the final state 6 in the interval 0 to 2 after applying this control function. This is another example. We have a pot of water filled by this T2 water inflow at the rate of R, and this is the concentration of the salt water xt and amount of salt water initially at this level, and the salt water outflow at the rate of R. What is the rate inflow? The same outflow. Both tapes are open and water through tape 2 is getting mixed into this solution instantly. The differential equation formulation is as follows. This is the differential equation of the model, and in particularly R is equal to 2, that is rate of inflow and outflow. V is equal to 20, initial condition is 0.5, then T belongs to the interval 0 to 6. The differential equation formulation becomes like this one. Then this is the trajectory path. Then final condition, it starts from 0.5 and goes to be 6. A trajectory of the system which is discussed by the. Now how much salt that should be mixed into the solution per unit time so that the concentration of the solution remains constant at time t is equal to 6 also. In order to sustain the concentration of the solution at t is equal to 6, we formulate the differential equation as follows by considering the control function u of t. This is the now this is the trajectory path. In earlier, the concentration of the salt water is this one, which is not to be desired. But after applying the control function, we get the concentration of the salt is maintained after point t is equal to be 6 also. Solution of the control system using these transition matrices. Consider the n-dimensional linear control system. This is the considerant. Then let phi t be the transition matrices of the homogeneous system. This one. The solution of the control system is given by this one. The control system, that is 14. Then the system is controllable if and only if this is the condition for arbitrary initial and final state x0, x1. There exists a control function u such that x1 is equal to be this one. This is a control function we have applied. The condition for the controllability. Now whether to check whether this function is controllable, then this is the condition. Condition is the system 14 is controllable if and only if the u belongs to the L2 such that x1 is equal to be this one, that is x1 like this one. Now to check the controllability, we define an operator C on L2 to R1 by defining like this one, like equation number 19, where C is bounded linear operator, range of C is subspace of Rn. Since x0 and xn are arbitrary, the system is controllable if and only if C is on to. Range C is called the reachable set of the systems. Now next, using this operator C, we form a controllability Gramian matrix. The controllability Gramian matrix is given by this one using the operator C. Then result, the linear control system is controllable if and only if this Gramian matrix is invertible and sharing control that move x0 to x1 is given by using this. This is a control function where b star is are the adjoint operator of this one. Next, controllability problem. Consider the linear system of equation using this condition where A and B are the matrices of order these two. Then Kalman rank condition, this system 22 is controllable if and only if rank of this B, augmented matrix B, AB, and so on. These are the augmented matrix. If rank of this is equal to be n, then our system will be controllable. And you can consider one more example, that is xt be the water level in tank 1, x2 be the water level in the tank 2. Earlier we have considered the same level. Then let alpha be the rate of outflow from the tank 1 and beta be the rate of outflow from the tank 2. Let u be the supply of the water of the system. This is the rate of inflow in the tank 1. This is the alpha is the rate of outflow, that is inflow in the tank 2, and beta is the rate of outflow of the tank 2. This is the mathematical problem for this model, and this is the matrix using this mathematical problem, and we can see using the earlier that Kalman theory, if the matrix, the rank of this B and augmented matrix B AB is equal to be 2, then this system will be controllable. The tank problem model 1 is controllable because as per the Kalman theory, rank is equal to be n. N means that is two equations, two variable x1 and x2, number of variables. Then we consider another model by which alpha is the rate of outflow from tank 1, and we place here as a u rate of inflow from in this 2, and beta is the rate of this 2. Then we form a model for this problem and find out the rank using the Kalman theory. Its rank is 1. It means this system is not controllable. This system is not consider a spring mass system having unit mass and with spring constant 1. Then you can find the model for this system by Newton's second law of motion. We have the following differential equation, and this is the Kalman theory. B for this spring mass system is controllable, and for this B, this system is not controllable. Next, we would like to define some different type of the controllability. First is exact controllability, steering of the dynamic control system from an arbitrary initial state to the arbitrary final state. This is named as exact controllability. Approximate controllability, an arbitrary initial state vector may be steered close to the final state vector. Then trajectory controllability may be also named as a T controllability, steering of the dynamic along a prescribed trajectory. Null controllability, any state vector may be steered to null vector. Finally, that is total controllability, steering of the dynamical control system from an arbitrary initial state to the arbitrary final state on each subintervals using the set of admissible controls is called the total controllability. These are the basic examples, or you can say applications of the control system. Controllability analysis can be made in many life problem like rocket launching problem, satellite control. If we would like to launch a rocket or satellite, if it is not controlled under the system, then it gives a harm to our system or a daily life to the human beings. Similarly, biological system, sugar level in the blood, normal fasting, that is 80 to 100, after eating, that is less than 180, 2 to 3 after eating, less than 130, and similarly inspired glucose. These are to be control points to be defined. This we have launch a missile, and the opposite side some enemy launch another missile, that is anti-missile. If these are not to be controlled, they are not to be heated to each other, otherwise they harm to be enemy and ours also. Economic, regulating the inflation rate. These are measures of the inflation rate, monetary measures, fiscal measures, and price control. Next, we would like to define the that is controllability of the fractional order system using the fixed point theory in finite and infinite dimension. This earlier we have defined basic introduction of the control theory, fixed point theory, and fractional calculus, and what are the major application of the control theory in the using the fractional calculus or using the fixed point theory. Then we would like to define some problem of the controllability in fractional order system using the fixed point theory. First problem is numerical approach to the controllability. Numerical approach to the controllability of the fractional order impulsive differential equation. We consider the fractional order non-linear differential equation with non-instantaneous impulse in space Rn. This is the fractional order nonlinear differential system where alpha belongs to the of order 1 lies between 1 and 2, and ut is the state function and time interval. This is 0. S naught is equal to T naught, that is less than T1, less than S1, less than T2, and so on, less than infinity. Let A be the coefficient matrix of the system 28. The control function U belongs to L2. We consider this fractional order non-linear system. Our aim is to solve this non-linear system, which may be used somewhere in the real life problem. In the real world life, there are many processes and phenomena that are characterized by abrupt change in their state. First is instantaneous impulsive. In this problem, we use the impulsive. That's why we'd like to define the impulsive. The duration of these changes is negligible in comparison with the duration of an entire evolution, such as shocks and the natural disasters. Non-instantaneous impulsive, the duration of these changes stay for a finite time intervals. A very well-known application of the non-instantaneous impulses is the introduction of the insulin in the bloodstream, which is abrupt change and the consequent absorption, which is a gradual process as it remains active for a finite time intervals. The function En was defined and studied by the Mittag-Leffler function in the year 1903. Because to solve this problem, we also use the Mittag-Leffler function. That's why we define here. It is a direct generalization of the exponential function. This is the definition for the Mittag-Leffler function in the series form. Whenever the series convergence is called the Mittag-Leffler function En. This is defined by En. The second is this En2 in the series is two-parameter Mittag-Leffler function with a parameter n1 and n2. The problem, which is nonlinear problem, first convert the nonlinear problem into the linear system. This is the fractional impulsive differential equation of order, which is a linear system corresponding to our system 28. First, our aim is to find the solution for this linear system, which is named as a mild solution for our system. This is a linear system corresponding to the nonlinear system. Then the solution of the system 31 is obtained by applying Laplace transformation method, and which is equal to be this one. This is the solution of this system 31. And then corresponding this system, we will find the applying the iterative scheme approximation techniques. We convert this linear system, solution of the linear system, to the corresponding our non-linear system using the iterative techniques, where the control function is this. This is the control function which is required to be solve our system of equations, non-linear system. Using this system to validate this system, I consider an example. Let us consider the fractional order impulsive linear system without control. This is the capital fractional order derivative of order 5 by 4. Then this is a function, and after solving this one example with the initial condition, these are the initial conditions, and we have ut is equal to this one, and other function which are to be used in our system are this. Let the final state will be this one. This is the final state, and you can see this function is not controlled. Our final state is this one. You can see in the graph, we could not reach on the final state at this point 10 and minus 10. It means system is uncontrolled. The trajectory of the impulsive linear system 35 starts from the initial state 02 and does not reach the final state 10 minus 10 on 02. It means we require some function. After introducing the control function Wt in the previous system, we have impulsive linear control system as like this one. And then after solving, you can see this system is controlled. Now it's final that the trajectory of the impulsive linear system starts from the initial state 0 and 2, and it reaches at the final state 10 and minus 10. 10, this is the final state 10, and this is the minus 10 in the interval 0 to 2, after applying the control function. The controllability Graamin matrix for this system is this one. It is clear that the Graamin matrix is non-singular. Therefore, the system is controllable in the interval 0 to. The control of the system 36 is given by this one. This is the control function. Control function Wt is given by this. After calculation of this one, one can determine the control function. And we consider one more example for the impulsive nonlinear system, capital fractional order derivative of this system. Then you can see comparing 37 and 28 with the original problem, ut like this one, another function like this one. This system is, our final state is 0, 5. Final state is 0, 5. But it cannot be reached at 0, 5. It cannot be. The trajectory of the impulsive linear system 37 start from the initial state and this one and does not reach the final state 0 to 0, 5 in the interval 0, 2. Then we apply the control function Wt in the previous system. Then we can see our system will be controlled in the interval 0 to 2. It reaches at the final state 10 minus 10. No, not 0, 5. It is our final state is this. This is our final state 0 and 5. 0 and 5 is the final state. 0 and 5. This is a 0 and this is 5. The system is controllable. Here B is this one. The controllability Gramian matrix for the system 38 is equal to this. And it is clear from the Kalman condition. And this Gramian matrix is non-singular. Therefore, under the assumption A3, A1 to A3, the non-linear system 38 is exactly controllable. In order to get total controllability of the non-linear system 38, we have the Gramian matrix. This one, these are the M0 and M32, and this our system which is to be controlled at the final state 3 2 by 2 2 respectively. The trajectory of the non-linear system 38 starts from the initial condition and reaches the final state and minus 2 2 in the interval 0 1 and the interval 0 2. This is our next problem. The next problem, that is approximate controllability. Kindly let me know the time for this, sir. Hello?
Sir, already you're running out of the time, sir.
Okay. This is the second problem. As we discussed earlier problem, the same is the second problem. Same like this one. First we consider the non-linear system, then we consider the corresponding linear system, then apply the control function, and we can validate our results using some examples. These are the results. This is the third problem, like the same as of the first problem, second problem, and mild solution is required after applying the control system. One can find the results, and these are the results. This is the fourth problem. Some basic definition which are to be required for solving these problems. You can see this is the conclusion of my talk. As we have seen that controllability has a large spectrum of the application in many real life problems, such as biological system, controlling sugar level in blood, economy, regulating inflation rate, ecology systems, pre-predictor model, which are described by the integer order differential system. Although integer order derivative and integral can be used to model many real-world problems, some anonymous processes have complicated dynamics that cannot be adequately described by the classical derivative models. In such models, fractional order derivative and integrals lead to a better understanding. So the study of controllability problems of fractional order system, such as delay, neutral, impulsive, and stochastic systems becomes more important, and research in this direction lead to some useful results. This is our conclusion of my talk. These are some basic references which I used in our talk. Thank you very much.
Any doubts from the audience?
Dr. Vats, I want to know
Yes, sir.
how these controlling systems are managed.
By how this
applying fixed point.
Some using fixed point theorem. I have already mentioned some of the fixed point theorem, because fixed point theorem guarantee us the solution of the system. That's why to get the solution, so our non-linear system convert to be first linear, and to apply the conditions of the fixed point theory, to check whether this linear system satisfy the conditions of the fixed point theorems. We use some Krasner-Selinsky theorem, Sauder fixed point theorem, and Banach theorem. Generally, we use three theorems to find out the system to be controlled, to get the solution of the control system.
I want to know whether the fixed point theorem we have, particularly one factor, that constant k or alpha, whatever we take, whether that is the controlling factor acting here?
Pardon, sir?
That in fixed point we have Lipschitz condition where
Lipschitz
this
condition.
alpha.
Yes.
Whether that alpha is taking care of that controlling factor?
Yes, alpha is taking care. Alpha is taking care to get the control function in the control function.
Okay, good.
Because only then the fixed point theorem can be applied.
Okay.
Yes, sir.
I think there is no more question. Dr. Shankar Raj, you can
Yes, sir.
thank you speaker.
Yeah. Thank you, Professor Ramesh Kumar, for your kind presentation, and